Let's now move on to virtual booth G. Thorsten and Damian, we can start to get ready. Booth G, inverter and electric motor design and testing, part of OBELICS. If I'm right, we now have Raul, Aida, Thorsten, and Damian. Is that correct?
Yes.
Okay, who is first? Raul, is that Raul I'm looking at now?
Hello, can you hear us?
Yes, I can. Okay, go ahead. The floor is yours.
Yes, here we are to Aida and myself that we are going to start the presentation, and then it's going to count Thorsten and Damian as well during the presentation.
Okay.
So here we are for presenting the activities in the cluster 4 of the OBELICS project that basically is dedicated to e-motor control, inverter design and testing. And this cluster,
this cluster is divided into these 5 use cases that we'll be presenting shortly.
Well, first of all, we want to mention that at the beginning of the project, we has seen the several challenges that we have to fulfill for the design and testing of inverter and e-motors. As Horst mentioned in the morning, we are now going to faster switching frequencies for in the case of inverters, and that affects also to the motors, and that means that we need to simulate our devices with a higher rates. And then we have seen these challenges at the beginning. We see that FPGAs is a solution for doing that, but nevertheless, this is a new work for the people that is developing models. And then we realize that have to be kind of methodologies in order to allow these persons to do that. And also the combination of these fast simulations with a slow simulation that combine multiple domains was also an issue to cover, and the automation of the tests that we have done during the complete development process. We have different test levels, and the transition between them needs to be more harmonized. And that's what we have covered in this cluster, all in all, and with different aspects covered for the different use cases. And as follows, we want to present 3 of those highlights because of the short time that we have for the whole presentation. We cannot go into all the details, but we want to give you a bit of an impression about what we have done in this cluster.
So for this use case, we have basically used FPGAs and system-on-chip devices, and to be able to present it in a bit of a faster way, we have categorized our processes into 3 main categories. The first one being the modeling strategy. So here we have analyzed different Simulink models and different Simulink blocks to check how well the code is being generated. Because we do know that HDL code generation is promised to be very efficient. However, it depends very much on what kind of blocks we use. And here we also saw that different configurations also meant that the code was much more effective, especially concerning pipelining. Then we have a second stage, which was the base development. And in the base development, we have developed in the FPGA firmware design. There we go, there's the base development. And in this firmware design, we added the possibility for the Simulink user to generate code for both the processor and the FPGA, and to do all of this from within the Simulink environment. And in this base design, we have also added different firmwares for ADCs, DACs, and these are all available once the developer has downloaded his code onto the FPGA and onto the system-on-chip device. And the final point is the end user support, because here is the point where we notice that Simulink developers and control engineers do need a bit of guidance when it comes to the different steps that have to be taken. And this tool does exactly this. So we have the different steps that have to be respected in this sense. And we also have developed an Excel-based interface definition, which means that the user can define the input and output ports within Excel, and this will generate then a model in Simulink with all the necessary interfaces. Additionally, we have also added some debugging features. So we have, for example, a snapshot mode and a snapshot buffer in the FPGA where we can capture real-time data, and then we can easily send this data out even over slower ports like a serial port, and the data will be still the same real-time data that we have seen on the FPGA.
Good. The next use case is going to be presented by Thorsten Fischer.
Hello, everybody. My name is Thorsten Fischer. I will present you the use case 4.3, which is in the responsibility of AVL software and functions in Regensburg, Germany. The title of this use case is High-Frequency Inverter Design and Testing. That means in the focus of the power hill usage. The target was the development of testing and calibration methodology for the inverter, which are used in different vehicle variants. And in addition, the back-to-back testing comparison to other test areas like the signal hill or the dyno itself. For example, also the comparison between the E-machine, the original E-machine, in addition to the E-machine emulator, the model of this E-machine behind. On the left side, the picture on the left side, you can see this test environment, which is already located in Regensburg. And on the right side is the testing methodology, our target, the front loading of test cases of different test areas or test environments to validate the electronic first before we are going to the next step of next testing environments like a dyno or an eDrive test bench. The achievement is the high flexibility. We reached the high flexibility to the usage of different E-machine models in the real-time test environment and the highly flexibility of these E-machine models. And we see a very early validation, a complete validation of the inverter during the product development caused by this front-loading effect. And in addition, at the end, we reached more than 55% reduction of testing effort, therefore reduction of testing time, and increasing, therefore, the efficiency in the test coverage. Thank you very much.
Okay, the third use case that we are going to show in this booth is going to be explained in a video by Damian Miljavec.
In this use case, we would like to present a real-time permanent magnet synchronous machine thermal hardware in the loop. The end user gives just 3 points as inputs, battery voltage and 2 points on user-defined torque speed curve. The outputs in the form of geometry, electromagnetic, thermal and aging models are formed. Further on, they are coupled into multi-physical high-fidelity PMSM model. This model is further on merged into software in the loop connected to the thermal hardware in the loop. The overall system is shown here. The user can, for example, drive the system with the vehicle pedals and observe as well as measure the behavior of coupled E-machine models in seal and hill environment and observe many measured quantities as temperatures, efficiency, and so on. Here we can see the system, which is composed of this machine, where the heat flux in form of power is transferred via this shaft into the cooling system, which is on the other side, this, let's say, white part. Inside is running the liquid. We will see some CFD analysis, which was also done within the project. And this water is further connected to the heat exchanger to remove heat. All measured data in form of temperatures are then connected to the software in the loop, where we can observe the behavior and the temperatures and the currents and also the torque, all the losses, also the vehicle speed is shown here, and some final overview we can see here. Thank you.
We have achieved to cover all these points that I mentioned at the beginning, and we have achieved what we promised at the beginning of the project in this sense. And I think now the time is over, and we just want to say thank you for your attention, and we're open for questions.
Thank you very much.
Thank you very much. Okay, we have a question from Alain. He asks, how can you implement a model in FPGA, single environment, coming from a co-simulation, multiple environment? Who would like to answer that?
Well, if I understand the question correctly, what we meant with a single environment was that we were using only Simulink because we are using other tools, but they are not visible to the developer because they're being run in the background. So this GUI that we have made does exactly this. This automates the process where all the other tools are basically set aside so that the control engineer can focus on his algorithm and doesn't necessarily need to know how to use all the other tools that are necessary to program an FPGA.
So how easy is it then for a modeling engineer to develop their own algorithm?
Well, it's not that very easy. It's definitely possible, but from our experience, especially what we have seen also now in the project, some guidelines are needed. So there has to be some kind of strategy that allows the user to generate efficient code, because some kind of code, it will be possible to generate. But when it comes to resources and how well the resources are being used in the FPGA, it could happen that at some point the user will run out of FPGA resources exactly because the code wasn't really implemented efficiently enough.
Okay. And a question for Thorsten, hope he's still there. What is the performance of your Power Hill test bench?
Yes, I'm here. Hi. Okay, during the OBELICS project, we have a maximum testing power of 320 kilowatts. Just now we are talking about to double it. And we have a performance up to 1000 volt on the DC side, 48 volt to 1000 volt. Therefore, we can also reach the 48 volt systems. And at the end, we can operate the devices up to 1200 amps RMS. But let me mention one small topic. Benjamin Zillmann has in his presentation one hint beside, is a challenge for this SiC inverter technology to bring this high frequency in this test environment. We had already this kind of experience, and we had challenges, and we found out the solution. And this is not only the high kilometer of length of high voltage cables, there's a little bit much more behind, but in the meantime, we have updated and upgraded the test bench together with our AVL colleagues, and in the meantime, it's not a big topic to operate also the SiC inverter or the high frequency, because the switching frequency, the gradients of the switching is make some issues on the AC voltage side, and this was a big problem in our test facility. But in the meantime, we have found out the right solution for that.
Okay. A final question for Damian. The permanent magnet synchronous machine demonstrator that you had there, what are the coupling data between Hill and SIL?
Hello, hello to everybody. Do you hear me?
Yes, can hear you.
Okay, so the flux generated inside the model, which is with heat flux, which is passing over the active part, that means the stator iron, to the housing. This energy is then transferred to the power transferred via shaft, as you saw, and inside is specially designed heating equipment, which heats up the housing with the same power as it was calculated. And the temperature, measured temperature of the housing and the coolant is then somehow connected back, forming as boundary condition for this multi-physical model.
Okay. Damian, thank you very much. Well, thanks to Raul, Aida, Thorsten, and Damian for your contribution. It's time for us to move on. Thank you.
Thank you very much.
Thank you very much.